Recording in progress.
Okay, thanks. Okay, we're recording now. I didn't say too much. So my original intent was to just talk about pointers in every language, what references are in C++ and how they're basically the same thing, and like good sort of conventions relating to both of those. But that very quickly, like, it started falling into the territory of this is too language specific. I didn't want that. And also it's just kind of boring. Like that's stuff that you would just necessarily get experience with if you write any sort of program. And so instead, what we're going to look at is like a little bit about pointers, but not how to use them, just what is actually happening under the hood when you do use a pointer, however you decide to use it. Can I scroll? Okay. So just a very super brief primer on what a pointer is in like 30 seconds. So memory in a computer is sort of this big block. We draw it as a block that starts at address 0 and then goes to some address X, just some big number. And it's all contiguous. And at each address, there is presumably some type of useful data. And a pointer is just the address where some data is located. And what that allows you to do is just, if you want to reference the same data in multiple places, you can pass the pointer to that data around instead of having to copy the data every time. And just one tiny bit of vocab is, if I say dereference a pointer, that means I have a pointer, which is some number, some address in memory, and I'm going to that address and getting the value stored there. That's what dereferencing is. It's just getting the value from a pointer. Okay. So we're going to start off by talking about function pointers. And again, I don't want to talk about how they're used necessarily, but just that they exist, first of all, because this is probably something that even if you've heard of, you've probably never used it. And maybe also don't understand how it works. And the reason I'm saying this is because it's sort of a nice introduction to today. It forces you to have this key realization about modern computers that I've brought up several times. Modern computers meaning the von Neumann architecture, where, which I'll define that later. So this realization is that all a computer does is move numbers around in memory. That's all it is. Data is numbers somewhere in memory. Code is numbers somewhere in memory. And if it's somewhere in memory, you can get its address. It's at some known location in memory. And if you have the address, you have a pointer to it. So what is a function pointer then? Well, if we think about it, our executable file, our actual program, is sort of separated out into a couple different chunks. There's a couple different types of like data sections. There's like a constant data one, a regular one, and like an uninitialized one or something. There's a lot. But generally, we can think of it as just all the data and all the actual compiled code, the instructions that will run on the hardware, the numbers. And if you think about what a data pointer is, if you have some array within here that's just a contiguous block of memory, you might have a pointer to the first element of that array. In the same way, if you have a function, which is just some contiguous block of instructions in your code, you can have a pointer to the first instruction of that function. And the reason it's the first is because it's all stored contiguously. That's a pretty basic thing, but keep it in mind because it sort of, I think, will answer a lot of questions that you might have about this stuff. Like, well, why does that work and all of this? It's because pretty much all the memory stuff we're talking about today relies on the fact that chunks of memory are stored contiguously, like an array. It's just all packed in right together. So if we have a pointer to the first instruction of a function, then all we have to do is tell the CPU, hey, execute that instruction. And then we're in the function. That's all it is. So we talked very briefly last time about the concept of an instruction pointer, which is sort of, it's a register. It's like a register on the CPU that usually you can't modify directly. You can like write certain instructions and CPU will modify it for you. In x86, this is called RIP, Register Instruction Pointer. It's also called instruction counter or program counter. They mean the same thing. And what this is just an address of the next instruction to be executed. And because this is only modified by special commands like jumps, there's an instruction called call in x86, which is used for actual function calls rather than just like branching. Because it's only modified through those special instructions, every cycle, I guess, by default, its default behavior is just to increment to the next address. Because remember, an address is just a number in some contiguous block of memory. And so if we are executing code, I'm sure you all know that code is executed sequentially. Again, it's not one of those things you really think about, you just take it for granted, but code is executed sequentially, at least in imperative languages. And so the instruction pointer just increments until it hits one of these special instructions that changes it to some value. And so if we have a function pointer, we can say, hey, I'll use the value of this function pointer, the number, the address. I'll set the instruction pointer to that. And then I'm in the function. I'm just executing, just going sequentially down the list. And that's sort of why you can have a function pointer, because just realizing that both of these things are just addresses in memory to some blocks of contiguous numbers, it sort of makes sense, right? Yeah.
So you said that's stored in the executable, but generally isn't like the executable stored like in your hard drive?
Yes, so this would actually be like a .exe file. Yeah. And then when you run it, it's sort of loaded from disk from your hard drive into RAM. Yeah. Okay. So again, I don't want to talk about these in any sort of concrete sense, really, in any language. They are useful though, so I will talk about like how they're used, not just the fact that they can be used. So these function pointers are useful in particular for creating things called higher order functions. And this is a concept that comes from functional programming, which is sort of a weird specialized set of languages that I don't know a whole lot about. But in those languages, you don't really have variables necessarily, certainly don't have objects. You have like a couple of primitive types, and then everything else that the program does, it does by just going through functions that you define. And because everything is functions, it's very, it's not necessary, but it's very convenient to be able to sort of pass this functionality around. And that's what a higher order function is. It's just a function that either takes another function as like a parameter, or it returns a function as like its return value, and then that function can be applied to anything else. And as for so this part actually is, there are analogs of this in all the imperative languages. If you've done anything in JavaScript, if you have like an array and you want to iterate over the array, usually you'll use like array.forEach, and then you will pass it a function. And what forEach does is it goes through every element of the array that you're calling it on. Let me write this down actually. So if I have like, oops, r.forEach, say I have an array of integers and I just want to print them all like that. So what this does is it says, okay, I have an array called R, and I will iterate over R, and for each element, I will pass it as an argument to this function that I've taken in as input. So for each is a higher order function. And there's all sorts of other ones. There's like map and filter in JavaScript. For each, a very similar thing exists in C++ in the STL. Now, these functions all are used to, they implement this concept of higher order functions, but they're not necessarily done with function pointers, especially in the more object-oriented languages. Java in particular, you can do stuff like this, but it's not a function pointer. The way it works, because Java is like super object-oriented, right? Like you can't just have standalone functions or anything. And so the way this would work in Java is there's some special syntax. I can't remember what it is. It's sort of like, I think it's like a list of parameters and then a single arrow and then braces and then the code. And this is called a lambda. And this exists in many languages. JavaScript, this right here, that's one form of a lambda. In Python, there's like the lambda keyword. C++ has special syntax for lambdas. And lambdas are basically just syntactic sugar for you. It makes it easier for the programmer to write. But when the compiler sees this, it will actually generate a unique type for this lambda. And all that type does, so if this is Java, this would turn into some like class. It'd probably have a bunch of weird underscores and like weird reserved compiler characters in it. And then it would just have a single method called like, I don't know, invoke or something like that. And it would have whatever list of oh my gosh, I can't write. Whatever list of parameters you specified in the lambda definition, and then the actual code as well. And then this sort of allows Java to get around the fact that everything is object-oriented, so it passes, instead of like passing a function, just passes an object that has this as a member function. And as I said, C++ has stuff like this as well. I just wanted to mention that because they are very similar and used to implement the same concepts, but still different under the hood. And by the way, raw function pointers are like way more efficient than passing around objects and stuff, at least in C++, because there's a lot of overhead with the way it does things. Anyways, we are now going to talk about virtual memory. So I sort of just introduced you there to a weird concept of pointers. Hopefully they got you to think about them in sort of a different way that you hadn't considered before. Now we're going to talk about what actually happens when I have a pointer and I need to use it. So like use it, meaning I need to get the value. I need to go to that memory address and copy the value. So there are several levels of this. The first is virtual memory, which is a system implemented by your operating system that you don't have to worry about. I don't even know if you can worry about it. I don't know if you can like hook into it at all. And then the second part is actually on the hardware, and this is caching. And we'll be talking about that afterwards. So these are somewhat similar, and both just sort of ways of like handling pointers so that you don't have to, basically. So virtual memory, to understand what this is, let's go back to last time we met when I said, okay, so a program, it has these registers. Obviously, that's where all the operations happen. But in terms of memory, we have the stack and we have the heap. And I just sort of said that. And I didn't like quantify or clarify what that actually means. And in your brain, you probably didn't have to ask what that means, right? It's just like, oh yeah, like my computer, it has memory, it has RAM, that's what it's for. So the stack and the heap are there. And that's true to some degree. But when it comes to dealing with pointers into the stack and the heap, the addresses that those pointers actually contain are sort of fake. They're virtual addresses into some virtual address space, which is a chunk of fake memory. It's also contiguous, so it goes from 0 down to some big number. And whenever you launch a program, or I guess launch a process, the operating system will create a virtual address space for that process. And all this is a it is a contiguous address space that allows for a non-contiguous mapping to actual physical memory. So this is 0 to some, RAM is also contiguous. It's address 0 to some like even bigger number, big X. And I might have certain chunks of my virtual address space that are sort of chopped up in weird ways, and they sort of point to different blocks within your physical actual memory. Okay. And this sort of goes back to what I mentioned earlier, which is that being contiguous here is a big advantage. That's sort of why this virtual address space exists in the first place, to the best of my knowledge. It's just a way for the operating system to make it easier for the programs running on that operating system to interface with the memory that is just going to be fragmented, because there's tons of different processes running and they're all using different parts of memory. So the next logical question, I think, is, well, how is this memory allocated then? Like, I've told you that the operating system will just give your process some virtual address space. And the address space is allocated in terms of pages. So a page is like the atom, I guess, of virtual memory. It's the smallest amount of memory that an operating system will allocate to anything. Because remember that the whole point of this is for the operating system to manage all of the computer's memory for all of the things that are happening on that computer. And if it has to worry about processes that are using, like 100 bytes of data, and it has to figure out how to sort all of these things that are 100 bytes wide, that's a really obnoxious, difficult problem. A, because it's not a power of 2, B, because they're not uniform, and C, because they're really tiny. So you will end up with super fragmented memory and everything slow down. But with pages, pages sort of set a standard size for chunks of memory. It's sort of like how an integer is just like a standard size in a program. It's like it's 4 bytes. That's what you get. A page, the size actually doesn't matter. It will vary per operating system. The only one I've seen before is 4 kilobytes, which is still pretty small. Like, that's a lot of data for a small program, but not a lot of data for a slightly larger program. So it's not like the operating system is wasting tons and tons of memory by just allocating things in multiples of this. And by that, what I mean is, if I have a program that requests, maybe it uses 200 bytes of data, the operating system is going to give it 4 kilobytes of data. It's going to give it 1 page. If it uses 4.5 kilobytes of data, the operating system will give it 2 pages. So it just rounds up to the nearest multiple of 4 kilobytes, or whatever the size is. Now, there's a slightly interesting thing that we will touch on here, just because it leads into the next section very well, which is, what if I run out of physical memory? So say, here's my physical memory, and all of this stuff is taken up. So that's physical. And then my virtual, maybe I need twice as much as I actually have left. So operating systems will solve this. They will still allow your program to run. They will say, okay, I'll give you whatever RAM I have left, but then also I will go to disk. This is a disk. And the rest of the stuff you requested, I'll just put that on the disk. You don't have to worry about it. So this is good and bad, because in like critical situations, it means that programs won't just fail to launch because you're out of memory. They will still, like, there's a backup mechanism there. But also, it's something that should be avoided at all costs, because it is very, 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 very slow. In fact, as we'll see in a minute, even going to RAM is quite slow. Going to disk, I don't remember the exact numbers. It's somewhere on the magnitude of 1,000 times slower than RAM, maybe 10,000. It's incredibly slow. And in particular, a problem you can run into is say that each of these like blocks here, each of those is just one page. So maybe I have like page 1 and then page 2, and I have an array that unluckily just happens to be like split between the pages. So maybe this is the end of my array, and then this is the start of my array, and they're in 2 pages. And then if I just want to write a simple program to like loop through the whole array and print everything, first, if like this is the start and then it sort of jumps here to this other page, first I'll go load page 1 and then read through all of that. And then I'll say, oh no, the rest of it is in page 2. That's on disk. So I have to copy page 1 to disk, copy page 2 to RAM. That's a lot of time. And this, in this case, obviously, this could be optimized by just making the whole array in one single page, just because the size worked out that way. Sometimes it can't be, you know, like pages are a set size of 4 kilobytes, so sometimes you just have more data. But when it can be avoided, this stuff should be. And we'll talk about how that is something that is important to understand, but that generally you don't have to worry about nowadays. Okay, so I think that's all I wanted to say about virtual memory. We'll look now a bit more at the von Neumann architecture, and in particular, the von Neumann bottleneck. That's what I've called it. I don't. That might be total gibberish, or maybe it's something that someone who knows what they're talking about coined. But the von Neumann bottleneck arises necessarily from the way that modern computers are built. So in the von Neumann architecture, we have like 2 separate components to a computer. We have the CPU, or the processor, which actually executes stuff, actually crunches the numbers. And then we have memory. And that's where all the numbers that the CPU executes on are stored. And also all of the instructions that the CPU executes, those are all stored in memory. And so we have this necessary sort of flow of data where we have to load instructions and data into the CPU. Yes.
So when you go to this,
Yes. Yeah. Right, because you don't want to, if you want to read data from that program, you don't want to have to go to disk every time. So it'll just load it to RAM for you. I think it's probably way more complicated than that, but in general, yeah. Okay, so our CPU, in order to do things, it has to load instructions and data from memory. And then if we want to use the values of those computations, we have to move the data back to memory. And this stuff is not free. This takes time. It's just copying data straight up. That's what it is. And that's why I said that even going to RAM from the CPU turns out to be quite slow, and something that is frequently optimized in high performance applications. But yeah, that's the von Neumann bottleneck. And the way we've sort of gotten around that, not gotten around it, but we've mitigated it to a degree, is by just sort of extending our CPU so that it's still a processor, but it also has a small amount of its own memory. And then what happens here is we have this sort of dual thing where the CPU loads instructions and data from main memory, but also from its own memory. And then it writes them back out to its own memory and eventually to main memory. So this is physical memory, RAM, or main memory. I will be using all of those interchangeably. They might have different definitions elsewhere. But what we're going to do now is look at this part of the diagram. This is called the cache. It is a chunk of memory on the CPU that is much smaller than main memory, which means it can be much faster. So I'll sort of draw for you this memory hierarchy. We have all these different levels. That's way too small. So at the top, we have registers. obviously it can't get much faster than that. These are single words for the most part, like 64 bits. They're right there on the CPU. That's what are used to do all the instructions. Right under that, we have cache, is sort of onboard memory of the CPU. And this is actually composed commonly of three different sections, L1, L2, and L3, which we'll look at. Then, another terrible line, then we have main memory or RAM. And then we have disk. And then I guess even under that, you have like network, like cloud stuff. And so we have this sort of interesting pattern where as you get higher up the pyramid, you increase in speed. And as you get lower, you increase in space. So that, yes.
Why is it random access?
That's a very good question. It's called random access because it is contiguous. Because if you have a contiguous chunk of memory that is addressed, sort of uniformly, then you can get to any location in that memory in constant time because it's just addition. So for things like arrays, which are stored contiguously, say I have a pointer to this element. If I want to get any other element, imagine this is like 1,000,000 elements long. If I want to get something in the middle, all I have to do is take my pointer to the beginning and add half of the length. And then that's just another address that I can go to and get it. It's not like a linked list where I have to start at the beginning and go through each one in succession. So that's why it's called random access, because it means that you can access any of it randomly and it'll take the same amount of time. But yeah, so this pyramid is pretty useful to have just like a general visualization of in your brain. It's the classic sort of time versus space trade-off that shows up literally everywhere. And that is something that I really, really want you to keep in mind for the future. Next time we're going to start, we'll look at like existing data structures, which will probably be a review for some of you, but hopefully I'll sprinkle some stuff in there that you may not have known. And then after that, we will be looking at how to design your own data structures and your own algorithms. And having this speed versus, or this time versus space trade-off like cemented into your brain is just necessary for understanding all of that. But okay, so we talked about this one last time. We sort of talked about these two today. Network I'm not talking about. Let's look at cache. Okay, so I sort of had, I don't know best way to go about introducing cache. So this won't flow very well, but all the information I think is valuable. So the first thing we'll talk about is the different levels. There is L1, L2, L3. Sometimes there is L4. Apparently that exists. I've never seen it. And I also don't know why we have 3 levels. That's just a magic number for some reason. It's what we've ended up with. I would imagine it just has something to do with tons and tons and tons of benchmarking that they've determined this. And they've also used that to determine the size. So the size of each cache is different. And what they contain is also kind of different. So the L1 cache is the fastest, but that also means it's the smallest. This is usually on the order of 100 kilobytes. It's actually basically always less than that, but it sort of gets up to 100, like 96-ish. The point is that it's tiny. 100 kilobytes is nothing. L2 is significantly bigger. It's about 2 to 3 megs usually. And then L3 is even bigger, on the order of 10 megs. And as we'll see in a minute, all of these they sort of act as backups for each of the other caches. But oh yeah, one last thing I want to mention is they all just store numbers, of course, but L1 usually has 2 separate areas, one for instructions, the instruction cache, and then one for data, like values versus instructions. The L2 and L3, it's all just a unified cache. Okay. So one thing, actually, I do have an interesting thing that I just learned recently about the instruction cache, which I basically just never thought it would exist, right? It's sort of the same thing of like, why would you even ask that question? It's just like, yeah, a computer runs instructions, of course, but they're numbers, they're stored somewhere. And so if you can cache those instructions rather than having to go to RAM every time you want to run something, it's way faster. So of course they do that. And on the Nintendo 64 in the late 90s, it had an instruction cache that strangely there was some weird combination of hardware where if you wrote a loop, like say you have like a 3-component vector and you go through, you just want to zero it out. So you say like v at I equals 0. This code, this actual loop, which compiles down to assembly that's basically like it has to initialize a counter, and then it has to go through the loop, make sure the counter is still less than 3. Then when it's done, it has to jump back to the top. That loop is actually faster than the unrolled code of this. And then those are all the same. And this is literally just 3 instructions and no jumps. Jumps can be slow because CPUs do this thing called branch predicting, where they try to determine ahead of time whether or not a jump will be taken. And if they're wrong about it, they sort of like preload instructions depending on their guess. And if they're wrong, they've just wasted a bunch of time loading those instructions and starting to execute them. So jumps can be bad. But anyways, this is 3 instructions. This is like more than 3. And jumps. And this one actually would run faster on the N64. Somehow its instruction cache worked in such a way that the body of the loop, the instructions in the body of the loop, were in the instruction cache. And so for each iteration of the loop, it didn't have to load any new instructions, because each of these instructions will be a separate thing, because they all have different constant values that would be stored as part of the instruction. I think that's my best guess as to why it works, but that's a very obscure thing. And it's also not true today necessarily. Like nowadays, loop unrolling, this bottom thing, compilers will do that quite often for you. If you have a loop like this, which is just going to run for a compile time constant number of iterations, if that number is small enough, then the optimizer will actually unroll it and just like copy and paste that same instruction however many times, because it's faster than jumping and keeping track of a incrementer and everything. But anyways, that's the instruction cache. Okay, so let's look at what the caches actually do and how they work. So I mentioned that they are sort of backups for each other. So draw it like this, where we have our CPU, we have L1, and we have L2, which is bigger, then we have L3, which is the biggest, and then finally, we have actual RAM. So when I have a pointer, and I say to the CPU, hey, go to this address and get me that value, the CPU says, okay, I have this pointer, I'll find that place in RAM, which is not a big deal. Like calculating the address it's supposed to go to is very easy. It's constant time because it is random access. It's all contiguous. But there is a significant amount of overhead in going to RAM because RAM is very big. And so it goes to RAM, and then it sort of would copy the data back to itself. But if I have an array of 1,000 elements, I have to do this loop 1,000 times, where I go to RAM, get one value, go to RAM, get the next value. That's terrible. So what it does instead is it says, okay, the CPU will talk to RAM, say, I need these values, and these values will be copied into the caches successively like that, and then transferred to the CPU. And like exactly which memory is in which cache at a given time is implementation defined. It's different for each CPU probably. there are tons of different algorithms controlling how that works. I don't find it particularly interesting. I think that's lower level than I really care to go. But if you're interested in that, you can just look that up on Wikipedia or something. I'm sure there's some good YouTube videos about it. But anyways, we don't care about how that works. We only care that what we're doing here is creating copies of the data in RAM, which is interesting because traditionally you're told that copying is bad. Certainly in like my line of work of game engine stuff, copying is like a death wish. Like if you're copying something of a significant size every frame, your game is just not going to run fast. But here, the overhead of going to and from RAM 1,000 times for each element in your array is actually slower than going to RAM just a couple of times and doing the copy from RAM to local storage. Okay, so when we go to RAM and we get some value, we don't just get that value. That's the next key thing. The first key thing is we go to RAM and we make a local copy of it for the CPU. The next key thing is that we get whatever value we're told to get and a bunch of different values around it. And this is a very similar concept to paging in virtual memory, where in that you get 4 kilobytes, that's sort of the smallest size, just because it sort of gives you some wiggle room, right? The same thing is true of caches, except it's not called a page, it's called a cache line, or I think it's also called a cache block. But as far as I know, those are the same thing. Again, the size doesn't really matter. Usually it's 64 bytes, I think. But what that means is if I have a pointer to some array and I want to get the first element of that array, say that this is memory, I have the first element of my array right here, I have a pointer to it, I'm trying to get it. Just say for convenience that this whole little box of memory I've drawn happens to be 64 bytes, then what is actually returned to the CPU is this whole thing. This whole thing will be moved into the cache. And what that means is that when I want to get the next value in the array, I don't even have to go to RAM, because I have a local copy of this 64 bytes, and all I have to do is say, okay, I'll go here, and it's right there. And the reason this works is because this memory is contiguous. It is 64 contiguous bytes. So when a cache line or a cache block is fetched from RAM and copied into the cache, obviously all of the data is copied, but also there is some metadata. There's way more than this, which has to do with the sort of algorithm I mentioned previously of how do you figure out what should be in any cache at a given time. But the one we're interested in is like the sort of base address of that block. And so this will be an address in physical RAM that is likely going to be aligned to a multiple of 64 bytes, just because that's the cache line size. And what this allows you to do, because it's all contiguous, is if I have this block of memory and I say, okay, my address, my base address is some value X. And I just got this, I just got a pointer to this. And now I'm looking for a pointer to the next element. The CPU can just look through all of the cache lines it has in its cache at that time, and it'll say, okay, for the base address is the, say I'm requesting, right now I'm requesting an address P. It'll just say if P is greater than or equal to a base address and P is less than a base address plus 64 bytes. If this is true, then P is already in the cache and I don't have to go to main memory, which saves a lot of time. And again, that only works because these are contiguous chunks of memory. Okay, oh, and I guess just some more vocab here. If this occurs where a value you're looking for is already in the cache, that's called a cache hit. And if it's not in the cache, that's called a cache miss. And you will probably hear that thrown around. This is actually something that people still worry about optimizing. even in things as simple as arrays, like the order in which you traverse arrays, especially nested arrays, can actually affect how many travels to RAM the CPU has to make, how many cache misses you have, and you want to end up with the highest cache hit rate. And of course, the algorithms for figuring out which cache lines should be in a cache at a given time contribute very heavily to the cache hit. Yes.
Yeah, I guess that's not. How do you consider that in your implementation if you have an array about like what element is in your
You said in your implementation. What do you mean by that?
Oh, like if you're actually implementing something and you want to be wary of that, like instead your elements in your array,
Right. So you're saying like, how do you know where they are, basically? Yeah. Okay, that's a great question. And I was actually just about to talk about that. So for things like static arrays, things that are just allocated, in sort of static memory as part of the executable, the optimizer, which is part of the compiler, will go through your program and it will look at these blocks of data and align them to cache lines. So if I have an array that is 64 bytes, say exactly the size of a cache line, and it's split, it's currently split such that like the first half of it is here and the second half of it is here. And the optimizer will just add a bunch of nothing to there. It'll basically just fill this with zeros to push everything else down here. And in that case, your entire array is in a single cache line. For non-static things that aren't allocated like within the executable, like on the heap, for example, it's up to the whatever heap management implementation you're using. You just sort of pray that it's good enough and that it knows what it's doing, which generally they do. But again, for things where performance, speed performance is very important, they often just write their own memory allocators. But yeah, does that answer your question? Yeah. Okay, cool.
So then, like, if you had an array that exceeded like a block size, and I guess you wanted to be, wary of that, there's not really. Oh, I mean, like, would there be a way to be wary that you had an array that was bigger than a block size, and you wanted to be efficient about how you're accessing it, so you did it?
Yes. So in that case, actually just sort of the default pattern of accessing it from front to back would work out best. Because if you just poke at it sort of randomly, you might hit some values that are in one cache line and some that are in another. But if it's split across two cache lines, you can go through half of the array, and that's all in one cache line, and then the second half all in another. So it's sort of that will minimize the number of misses you have. Okay, cool. So I say that like we don't really have to worry about alignment because the optimizer does a lot of that for you. But you may have actually had to worry about this for your computer architecture class. In MIPS, like if you have like a .data section and you're trying to define an array, I don't remember the exact syntax for that. But usually before arrays especially, or any other variables, oftentimes you will do a dot align, I think is like the assembler directive, and you will tell it some number of bytes, and that will do exactly what I just described. It'll pad. So if I if I have, say, a word here, which is 4 bytes, and that contains some value, whatever. And then next I want to store a Q word. That's confusing, but just something that is 8 bytes. Then if I were to just pack these in together, what I would end up with is 12 bytes, so from 0 to 11, where the first 4 is this word, and the second, or the remaining 8 is this quad word. And this is sort of, it is relevant to what we're talking about, but it's sort of different. It's like a different type of optimization. This has to do with alignment of memory, where CPUs, I don't want to say expect, because in general that's not true, but they prefer if when they're operating on some chunk of memory, if the start of that memory, the start of whatever data they're working on, the address of that is a multiple of the size of the type in bytes. So let's see what that looks like. So a word is 4 bytes. A quad word is 8 bytes. I guess I'll just call this a D word to make it less confusing. In MIPS, 4 bytes is a word. In x86, 4 bytes is a D word. But anyways, so what I have here is, say this is 0, and then this would be 4, like the start of this quad word would be 4. So say that these are my pointers, just for simplicity's sake. My addresses are 0 and 4. So this checks out because a D word size is 4 bytes, and 0 mod 4 is 0. This one does not work because the size of a Q word is 8 bytes, and 4 mod 8 is 4, which is not 0. We want the starting, like the base address of a given chunk of data to be a multiple of the size in bytes of that data. And this, again, that's something that in higher level languages, they will figure that out for you. The classic example actually is like structs in C and C++. So if I have a struct, I don't know, S, and then I have like a char C and a double X, then what is the size in bytes of S? Well, you might say, okay, a char, that's 1 byte, and then a double, that's 8 bytes, so 9. Well, no, because it's smart and it will align this correctly. So you actually end up with something that looks more like this. So you have your char C, so that's 1 byte, and then you have char padding. You have 7 bytes of padding that is completely unused and actually inaccessible to you. Technically, by name, it's inaccessible. And then you'll have your double. And this whole thing, instead of 9 bytes, takes up 16 bytes. But again, that's so that it is friendly to the CPU. And this is something that I don't know enough about how the CPU deals with unaligned memory to like actually tell you that much about it, unfortunately. What I do know, though, is that in many cases, for other similar types of things, for just like operations that the CPU isn't necessarily designed to do, these can be like actually insane performance hits, like an order of 10. Like it will run 1/10 the speed of if it were actually aligned. And again, for alignment, I'm not sure if that's an accurate number, but there's this other thing, which I think I will talk about because I'm almost out of time. So I'll just sort of wrap this up. We talked about floating point numbers, how those are stored, specifically the IEEE format, where you have like 3 components to a floating point. I'll just use 32 bits, so a float. You have a sign, which is 1 bit. You have the exponent, which is 8, and then you have the mantissa, which is 23. And if I have a value, if I have a mantissa value that's like 1, 1, and then zeros, then this corresponds to a value of 1/2 plus 1/4 equals 0.75 in decimal. But there is like this implicit leading 1 in the mantissa that is used to actually get you an extra degree, not an extra degree, an extra digit of precision at the end. So really this becomes 1.75. But there's a certain class of these floating point numbers, again, in this format, where if you're trying to represent a number that needs an exponent smaller than is allowed by the 8 bits. So for 8 bits, the range of the exponent would be -128 to 127. If I'm trying to represent a number that's like 10 to the minus 200 something. Actually, that's a bit confusing. I'll say 2 to the minus 200. Then clearly I cannot represent that because the smallest value I can represent normally is 2 to the negative 128. And so what you end up with is you have what's called a denormalized number. They're also called subnormalized, which is weird. And essentially what that is you end up with a mantissa that doesn't have a leading one. That's the only way you have left to get smaller. You're already at the smallest exponent. So all you have to do, or all you can do, is remove that leading one and take this value. And for whatever reason, in the inner circuitry of the CPU, it's not designed to deal with that. And so traditionally what it would do is it would use sort of software routines basically to perform floating point operations on denormalized numbers. Now, floating point operations are already slow, but doing them in software when they should be done in hardware is a million billion times slower. Not really, it's about 10 times slower. So really, really bad. And nowadays there are certain flags in the CPU that you can set. In particular to the x86 instruction set, they've added these floating point specific extensions. In the late 90s, it was called SSE, streaming something. They're basically just SIMD floating point instructions. And then the newer ones are called AVX. There's AVX2 and AVX 512. And those just add faster floating point operations, bigger registers. You can pack multiple values in together. Pretty much they're designed for games actually. But you can set certain flags on the CPU. I think those flags came about within these extensions that say hey, if I get a denormalized floating point number, do one of three things. Either treat it as normal and do your slow software thing. B, just flush the value to 0, because if it's denormalized, it's going to be really tiny, right? So you can just say, oh, I don't care, that's 0, I don't need the accuracy, and that makes it way faster. Or C, throw an error, crash my program. This should not have happened. Just get rid of it. And so I don't think anything that catastrophic can happen if your memory isn't aligned properly. But there is a reason that compilers will pad out your structs like this. The anecdote I wanted to tell you, but I ran out of time, was about something with a GPU. And when you are communicating between two completely different processors with two completely different sets of memory, alignment is super important. It's very, very common in graphics libraries, especially for beginners when they're trying to send data from the CPU to the GPU, that they either specify the wrong number of bytes, or they forget to add padding to their data structures, and then they just basically end up with garbage data on the GPU, and it's incredibly difficult to debug. But anyways, that's a story for another time. I guess I could tell that. Probably not next week, maybe at some point in the future, I'm not sure. But that's all I had about pointers and caching. Hopefully this was valuable. Again, I think I said this quite a few times today. In general, you do not have to worry about all of this, but understanding it is very important. The anecdote I was going to tell is of a time where I was working with a GPU, and I didn't understand how a certain structure was used with regards to the caches. One of them was stored in L1 cache, and the other is stored in RAM. And it turns out that the one in RAM was twice as slow as the one in the cache. And that helps me solve the problem, because normally that's a super frustrating bug that you can't really debug, because it's nothing that you've done wrong. Your code is completely fine. All the data is fine. It's all aligned properly and everything. It's just that the way that the processors on the GPU are accessing this memory is such that it's slower. And I wouldn't have been able to figure that out or debug that or solve that problem if I didn't understand to some degree what the hardware is actually doing. Okay, so that concludes this. This is like the last of the low level stuff that we'll be talking about. Next week, as I mentioned, we will be going through a bunch of common data structures. I'll talk about some implementation, like typical implementations of them, typical operations on them. I'll also, it just occurred to me, I think I've talked about time complexity probably every single time. I don't know if I formally introduced that, so I'll definitely do that next time. And then after that, that'll just be one thing. And then we will go into actually designing data structures. So I'll have like some cool example problems of stuff that I've solved, data structures I've created to solve it, and algorithms that operate on those structures. So yeah, I hope to see you then.